Yeah, so see my kitchen and things behind me. You do the washing up. First of all, I guess I wanted to say thanks to David Barclay for reaching out, and for everyone at Dalhousie for inviting me to give this talk. And second, you might notice that the title at the top there is slightly different from the title that was sent out. I had a think about the initial title, which was The Importance of Biology for the Global Carbon Cycle. And I was going to talk about, I had grand plans to talk about my PhD thesis in its entirety, or give some kind of paraphrasing of it. And then I thought, well, it's a virtual seminar, so actually maybe I'll change my mind and talk more about a particular part of the thesis. So today I'm going to give the culmination of, the final PhD chapter of my thesis, which was published late last year. And it's called The Role of Nitrogen Fixes for Glacial Atmospheric CO2 Drawdown. So it is much like the biological importance for global carbon cycle, and I will delve into that a little bit. So underneath you'll see that in parentheses that I'm talking about unifying the biological contribution at high and low latitudes. And so here I'm talking about, what I will talk about is specifically the validity of low latitude drawdown of CO2, which has been debated. But then really at the end of the day we kind of come towards this idea that the high and low latitudes are both acting in the same direction, and they're both drawing CO2 into the ocean during the glacial period under this umbrella of ion fertilization. And I'd also like to shout out to Xana Chase and Rich Mattia particularly, and also Stephen Phipps and Nathan Bindoff, who were my committee on this project when I was at the University of Tasmania. Finally, as well, I'd also like to shout out to Al, my advisor currently at the University of Liverpool, and we're doing some good work, pretty exciting work, looking at nitrogen isotopes and their use into the future, which is kind of a different way of thinking about it. So looking particularly at some exciting work about using nitrogen isotopes to detect changes as a very sensitive detection of changes in net primary production, but that's for another day. So with that, I'll get on with it. We've been obsessed by the glacial cycles for decades, right? I mean, ever since there was a paper in 1982 that reconstructed the first glacial cycle going back 40,000 years, so glacial maximum to present atmospheric CO2. And since then there's been a raft of papers looking at the glacial cycles and reconstructing them back to 800,000 years. And so what I'm showing you here is these characteristic sawtooth glacial cycles going back 400,000 years in the top plot, and in the bottom plot you're seeing the relative change in temperature. And so we go from these mild interglacial periods where atmospheric CO2 is roughly 280 ppm, and then we sawtooth down in this long cycle, roughly 100,000 years, into a glacial maxima, which are reoccurring and highlighted by the grey bars of CO2 minima, temperature minima. And so the nature of these cycles, how regular they are, prompted a lot of people to look for a silver bullet solution. So a lot of people talking about, I've been told a lot of people were looking for a silver bullet solution about how there would be one possible solution to cause this reoccurring behaviour. Because the probability of there being lots of different pieces to this puzzle and them all lining up in the same way, exactly the same ways every time, is a low probability. But as time's gone on and research has been done, it seems like there's a lot of pieces, actually. The latter is true, and there's a lot of pieces to this puzzle. And we're still obsessed with it. Like we are still unsatisfied by the current explanations we have, although we have a lot of them. So, with that in mind, I will talk quickly about some early theories. So, we recognised pretty quickly that the ocean was important. The ocean has a high potential to sequester CO2 and hold it there permanently, both because of its volume and also because of its chemistry. And some early theories seized on the biological pump, specifically within the ocean, to think about how carbon could be permanently stored in a glacial climate and stored away from the atmosphere. And so here, even in these early theories, we can look for both high latitude processes, such as this paper from Danny Sigmund and Ed Boyle, that looked at the obvious candidate of macronutrients in the higher latitudes being underutilized and the biological pump being inefficient. And therefore, if you could somehow make that biological pump, those phytoplankton more efficient, then you would reduce the leakage of CO2 out of that these high latitude zones. And then there was also papers like the one by Paul Falkowski in '97, which was theorizing how if the dusty glacial conditions and nitrogen fixers tend to like dust, and so if you could somehow stimulate nitrogen fixation, that would stimulate nitrate addition to the surface ocean where it's most needed, and thereby facilitate carbon drawdown. And so I guess what I put here is this schematic of the biological pump, or my likeness of it. And you can see that there's an area on the right with CO2 outgassing, and then the biology kind of grows and sucks in CO2, which is then sequestered within the ocean interior through sinking. And in my understanding of it, if you were to shift those biology, I use my cursor, I suppose. Yeah. If you were to shift that biology over a little bit towards this area of CO2 outgassing, for instance, in the equatorial Pacific, if you were to shift that biological production over to the CO2 outgassing region and then increase its efficiency, say by increasing the C to P ratio, or increase the length at which these down arrows go down into the deep ocean, therefore sequestering it for longer, you could actually trap more CO2 into the ocean. Right, so that's kind of my schematic first up of the biological pump. Right, onto numerous pieces. So I mentioned before that we have numerous pieces to this glacial CO2 puzzle. We have reorganizations of the ocean circulation. This is obviously a big one. And within this one big piece, we can say that there's increases in sea ice, there's salinity stratification in the ocean, which reduces the mixing in the deep ocean. Also reduced topographic turbulence, as we have an increase in the volume of, say, Antarctic bottom water that fills into the lower overturning cell, raising the boundary between the upper and the lower overturning, that then reduces the influence of topography and stirring. That could increase, say, the amount of carbon that's sequestered in the deep ocean. An equatorward shift in the westerly winds, and also a decrease in their magnitude, which could also reduce the stirring in the ocean interior. And so all of these things, they're all important, and there's been numerous papers talking about them and kind of working out the details. But in all, I think the most important point is that the ocean circulation slows down, and that is strongly supported by reconstructions of ocean oxygen concentration during the LGM, the last glacial maximum, that suggests that there was this reduction in ocean overturning. So that's a really important piece. Then we get into the biological pieces, which of course is my focus for today. And so the second part here that I'm showing is temperature-dependent remineralization. So a cooling of the global ocean will cause a reduction in remineralization rates. And that reduction in remineralization rates is due to the reduction of metabolism by heterotrophic bacteria, etc. And so that would allow a lot more of whatever carbon is produced, organic carbon is produced in the surface ocean, to actually drift deeper into the deep ocean as it sinks. Another theory is the greater organic carbon relative to inorganic carbon production rate. So if you were to, say, increase the amount of organic carbon production relative to inorganic carbon, you do two things. You not only reduce the amount of CO2 that's outgassing the surface ocean by reducing relatively the amount of calcium carbonate that's produced, but you also increase relatively the amount of alkalinity at the surface ocean through the formation of organic carbon, and therefore increase the amount of CO2 that's ingassing. So this is another way that you could increase CO2 in the ocean. And fourth, which is one that I will focus on, is ion fertilization. So we have two parts of this. First of all is ion fertilization of eutrophic regions. These are regions like the Southern Ocean, the subarctic Pacific, the equatorial Pacific. And first officially recognized by Martin in 1990, this is kind of an obvious one where, if you, like I said before, if you were to increase the utilization of macronutrients which are in surplus in these regions, well, you would increase the amount of carbon that was sequestered. You'd actually tighten the lid, I suppose, on that CO2 that's outgassed in these regions. And secondly is the nitrogen fixation hypothesis proposed by Falkowski, and actually followed up by Keith Moore, who looked at some decadal changes in the nitrogen cycle, which was more of a present-future study, but nonetheless found a connection between nitrogen fixes and CO2 in the atmosphere. Right, so what do you learn from all this? I mean, maybe some of this is not actually news to a lot of you, and I'm just going over the background. But the magnitude here is not an issue. We have all these pieces to the glacial CO2 puzzle, and as highlighted by this paper by Galbraith and Skinner published earlier this year, they really emphasize that additional mechanisms are not necessary, I suppose. You could argue either way, but I don't think they're necessary, and probably what we need to start doing is putting the pieces of the puzzle together. So I've got all these puzzle pieces, and what would be useful is actually to put them together. And so I'm going to argue that I'm trying to do that in this study. So a good candidate for putting the pieces of the puzzle together is to look at forcings of the ocean. So what are the things that we know happen to the ocean? And one of them is dust deposition. So I'm going to go back to number 4 here, and then look at this on a global perspective, I suppose. So there's this really interesting study by Martinez Garcia, which looked at the transition from the glacial cycles from both before and after the mid-Pleistocene transition. So the mid-Pleistocene transition was characterized roughly a million years ago, and it involved the transition from glacial cycles that were roughly 40,000 years in duration and roughly 60 ppm in magnitude of CO2 to 100,000 years in length and roughly 100 ppm in magnitude. And that's what you're seeing here in this figure. And these longer term glacial cycles which characterize the most recent ones. And if we look at the dust records of this period, not only did they increase at the mid-Pleistocene transition, but they continued to stay prevalent, and most prevalent during the glacial maxima. And so what was argued in this paper is that the dustiness of the atmosphere and the delivery of dust to the ocean was key to the deepening of the glacial cycles. So one thing that we can learn from this potentially is that we could say that the glacial cycles prior to the mid-Pleistocene transition may have been forced by purely physical mechanisms. So 60 ppm roughly, you could say, is physically driven, reorganizations of the ocean circulation, etc. And then the deepening of these glacial maxima, which characterize the most recent ones over the last 800,000 years, you could say are probably 30 ppm, characterizing the last 30 ppm to get to 90 ppm of the total glacial magnitude. And so some papers have tried to partition the physical versus biological contribution, and so we have generally at least 30 ppm is considered to be biological. So how can we explain this under the dust deposition umbrella as one of the most kind of what's the word? Well, it's an obvious candidate. Let's go from there. So we have two pieces to this sub pieces to this iron fertilization mechanism. So we have a high latitude piece. This is obvious. I've been talking about this previously, whereby if you were to utilize the nutrients in the Southern Ocean, then you would have a mechanism by which you could tighten the lid of CO2 outgassing. And so the potential for this is huge. 70% of preformed nutrients exist in the Southern Ocean. And preformed, what I mean by preformed nutrients is a nutrient that has been utilized by biology and then remineralized in the ocean interior, and then the nutrients being released. That's not preformed. Preformed nutrients are nutrients that have not gone through that phase. Sorry. So what that means is that these are just nutrients floating around that haven't been utilised by biology. And so if 70% of them are available in the Southern Ocean, this means there's huge potential for an increase in the efficiency of biological pump in the Southern Ocean. And this hypothesis proposed by Martin in 1990 has largely been turned into theory. And quite nicely, I think, by this paper by Martinez Garcia, which was located in the South Atlantic, in the subantarctic Atlantic. And on the right, I'll just bring my cursor up. On the right, here we see the CO2 cycle over the last glacial cycle, with the CO2 minima during the glacial maxima. And at this core, they find in the ion flux to that core, is shown in the black, and in the red, with this really uncanny pattern following it, is the proxy, delta 15N proxy of nutrient utilization, so nitrate utilization. So this is showing that the agreement between ion deposition to this site, ion fertilization, and nutrient utilization is very tight, suggesting that there is a mechanism at play here that's working to draw CO2 into the ocean. But there is this inconsistency, right? So recent modelling studies have struggled to actually replicate a strong response in terms of carbon dioxide drawdown via aeolian ion deposition to the ocean. So these studies find less than or equal to 10 ppm or drawdown through ion fertilization. This is a problem, right? So it's inconsistent with this 30 ppm we've assumed to be due to biology. And so the excess macronutrients are possibly not being consumed to the amount that we would want in order to explain this biological contribution. And so I think there are many reasons actually to look to the low latitudes, and I'll try and convince you of that. So here is a figure from Kofeld 15 years ago and published in Science. And there's been other papers to confirm this, that the low latitudes, as well as the subarctic, Antarctic, have experienced an increase in carbon export during the glacial period relative to late Holocene, or relative to modern. You can be thinking about that as modern day. And so the red circles are areas where carbon export increased during the glacial period, and you can see that there's quite a few of them in the low latitudes. Secondly, the low latitudes, particularly the tropics, represented in the yellows and reds, represent over 2/3 of outgassing of carbon dioxide from the ocean globally. So if you were to somehow tighten the lid of CO2 outgassing via biology, more efficient biology, you would sequester more CO2. And possibly one thing that is not considered so often, potentially, is that phosphate in the tropics, although it's dwarfed by the amount of phosphate in the Southern Ocean and the subarctic Pacific in the high latitudes, is in excess quantities, so it's in surplus. So you see in the tropical Pacific and the Indian Ocean and somewhat in the tropical Atlantic, values of phosphate in excess of 0.2 micromolar. And this, I would argue, and so it spreads out 10 to 15 degrees either side of the equator, and this, I would argue, is unrealized potential for an increase in the efficiency of the biological pump that could be prevalent over glacial and interglacial cycles. Fourth, there are high carbon to phosphorus ratios in marine communities that inhabit the low latitudes. There's been lots of research recently, this has really exploded, I suppose, this variable stoichiometry arguments, showing that in the low latitudes, in these warm, nutrient-poor regions, there's incredibly high C to P ratios, up to 140, 160, 180 to 1, suggesting that if you were to increase biological productivity in these zones, then even if just a little bit, you'd still be increasing the amount of you still increase significantly the amount of carbon that was stored in the ocean, because the C to P ratios are higher than the mean DIC to phosphate ratio of the ocean. And this is particularly so for those fertilized by iron. So in areas where there's iron fertilization and there's very low phosphorus concentrations, the carbon to phosphorus ratios tend to peak. And finally, there's also regions in the low latitudes, the oxygen minimum zones, where there's a really strong downward transfer of organic matter to the deep ocean. So this is a plot from De Vries in 2017 showing that their estimate for the transfer efficiency of organic matter from the surface ocean, or 100 meters to 1,000 meters. So anywhere that's in the warmer colours, getting up to 0.4 or 40%, means that there's a certain amount of organic matter that is a certain proportion of organic matter that's transferred, that makes it from 100 meters to 1,000 meters. So at 0.4, for instance, in the eastern tropical North Pacific oxygen minimum zone, you can see that roughly 40% of the organic matter at 100 meters makes it to 1,000 meters. This is an incredibly efficient way of getting carbon from the surface ocean to the deep ocean. And this has been shown in other papers, for instance by McCavan, looking at the zooplankton role in this, and then also Frank Pavia using thorium isotopes. So what I'm going to argue is that nitrogen fixes are actually a perfect candidate for a low latitude drawdown of atmospheric CO2. They're a perfect candidate because they like dust-borne iron. So during a glacial period when there's more dust, they will be fertilized by iron. Where they occur, they tend to draw down phosphorus to very low levels. They supply nitrogen, which is needed across the low latitudes, and limits most communities in the low latitude ocean. And through being fertilized by iron and then drawing down phosphorus, they increase the C to P ratio of phytoplankton and therefore should increase carbon export through the interior. Now, if this happens close to, for instance, the Eastern Pacific, where there's an increase, where there's low oxygen concentrations already, then that should cause this, there should be this pathway whereby carbon is really rapidly transferred to the deep ocean. And so through this mechanism, we're testing the original proposal of Falkowski and trying to quantify its importance. So I think that I'm going to go through quickly the reason why they're ideal candidate and actually provide some citations to support my argument. So first, they're physiologically adapted to use iron and dust particles. I think this is so cool. So there's been lots of papers recently showing this, the most recent being Noel Held's PhD thesis. This is a really cool animation of a trichodesmian colony that is actually working, all its bacteria and its filaments are working together to actually take dust particles and move them into the center of the colony where they can extract the minerals they need, for instance iron. So yeah, drawing attention to Noah Held's PhD thesis, which is published just this year, she talks about this in her fourth chapter. So this is a real thing. Second, where they do exist, they are incredibly efficient users of phosphorus. So they have a physiology that allows them to take up all forms of phosphorus, organic and organic. And they tend to, where they exist, they tend to draw it down to very low levels. Because of this, they are cosmopolitan inhabitants of the subtropics and tropics. And where they do exist in high concentrations, they can contribute up to half of primary production. Finally, they also have significant carbon fixation themselves. So their carbon to phosphorus ratios are well in excess of the mean DIC to phosphate ratios of the global ocean. They, in the model that I'm going to show you that we use for this study, we set it at 330 to 1, which you'll probably think is incredibly high, but actually there's been measurements of trichodesmium that have carbon to phosphorus ratios of 800 to 1. So even if there's no primary production going on in the other part of the community, other phytoplankton, these cyanobacteria can actually have significant carbon fixation potential themselves by just if some of that carbon actually makes it down below the mix layer. And so what we have is the necessary ingredients, I think, to argue that for this low latitude mechanism to complement what we know of high latitude potential for dust fertilization. We have this response of nitrogen fixes to dust. We can have high carbon to phosphorus ratios and low phosphate environments, and we can have a strong downward transfer of organic matter in lower oxygen waters. Now, all these things should work together in a glacial scenario, where we have dust deposition, we have stratification that should lower phosphate concentrations, increasing C/P, and we also have a decrease in the amount of oxygen in the global ocean. And so we go ahead and use this model, which is something that I developed during my PhD, and the description of these various things, so variable stoichiometry and variable renormalization rates, the introduction of a dynamic nitrogen cycle, etc., was described in this paper published 2 years ago. So we're going to use this as the foundation for which to do our investigation. And we're going to use this model to answer 3 questions. 1, how do nitrogen fixes strengthen the biological pump? I suppose this is the mechanism, right? So this is actually testing whether a mechanism exists. And it's a bit like going back to that Martinez-Garcia paper of 2014. They found evidence of the mechanism of nutrient utilization increasing under dust deposition in the subarctic Atlantic. And so that was kind of the confirmation that it actually happens. Second, though, we're going to go further because we have a model, and we're going to look at how much carbon dioxide this mechanism actually sequesters. How important is it? How much CO2 actually gets into the ocean through it. If it's 1 ppm, who cares? 3, is there any evidence in the paleo proxy record for this actually happening? Because if we can prove it in a model, does that actually mean anything? It doesn't mean anything unless we can say that it lines up with proxies, or it makes sense with the environments that we know were prevalent during the glacial period. So we're going to use the delta 15N proxies, the nitrogen isotope proxy record, the global proxy record, to actually test whether this mechanism is real. And just before we go on, what we did was we took this global ocean model and then we replaced the iron deposition from the atmosphere with the glacial one. And so wherever I've done that going forward, just remember that it looks like this. So this is the glacial to the modern, relative to the modern deposition field, and you'll see that it's highly variable. So in some areas, the factor increase, which is represented by the dark colours, so the factor increase can be up to 40 times the modern deposition rates, for instance, off Chile there. But in the equatorial Pacific, it can be only up to 5 times, in some places only twice the rate, and this is consistent with previous studies looking at, say, accumulation rates in the equatorial Pacific and the tropical regions. So, in answer to our first question, can nitrogen fixes strengthen the biological pump? The answer is yes, and I'm going to take you through the reasons why that is the case in the model. Right, so what we find is this shift in nitrogen fixes. That's the most important point here. There's a global increase in nitrogen fixation rate of 32 teragrams of nitrogen per year, but most importantly, what you're seeing is a difference between a modern and a glacial iron deposition rate. So the blues are where nitrogen fixation has decreased under the glacial iron fertilization scenario, and the reds are where they've increased. And the biggest change is in the Pacific, where we have this shift from the northwest to the east in to surround the upwelling zones. And what I'm calling this is a stronger coupling between nitrogen fixation and denitrification. So if you relieve nitrogen fixes of their iron requirements by fertilizing them with enough iron, then the only things that control where nitrogen fixes are is phosphorus and nitrogen. So they need phosphorus and they need low nitrogen. So where do they go? They go to a place where there's high phosphorus and low nitrate. And where does this occur? In the denitrification regions, where denitrification in the suboxic zones strips the water of nitrogen while enriching it in phosphorus through the process of remineralization. So the nitrogen fixes migrate in the model to bound the upwelling zones in the eastern tropical Pacific, where denitrification rates are highest. And the place that, so the delineation between where nitrogen fixation has increased and where it's not changed, around that, I'm going to use my cursor. So the place where it hasn't increased, there's ample nitrate here, and then as nitrate is consumed, it goes to 0, and this is where nitrogen fixation increases and then consumes the available phosphorus. And so we see this in the change in surface phosphate. So surface phosphate globally has not decreased that much, but regionally in the Eastern Pacific, it decreases quite a lot. So we get roughly a 0.2 in some areas decrease, 0.2 micromolar decrease in phosphate. And that's consistent where there's an increase in nitrogen fixation. The decrease in phosphorus then increases carbon to phosphorus ratios in line with what we know in the field. And that increase in C to P ratios of the community increases the amount of carbon export that occurs in that zone. Even though global ocean carbon export decreases slightly, these large increases happen in the vicinity where nitrogen fixation increases. And at the same time, there's a vertical expansion in the oxygen minimum zones, which is consistent with previous work looking at the vertical expansion of oxygen minimum zones during the last glacial maximum. And all in all, what we find is that there is this bulk transfer of carbon into the deep ocean, in the deep Pacific, and that bulk transfer in that equatorial zone, or that tropical zone, then moves out and spreads out throughout the wider Pacific basin. And this is again consistent with numerous studies looking at the amount of respired carbon in the Pacific and how it increased during the glacial period. And so the answer is yes. Can nitrogen fix the strength of the biological pump? And yeah, let's keep going. So the second question is, how much CO2 can nitrogen fix the sequester? It's all well and good to look at this and say, yeah, there's a mechanism and it's, it is a model, so you can say yay or nay. But the next thing to do is actually look at quantifying whether this is important or not. You'll see previously that you might have been surprised by the actual amount of carbon that was sequestered here. 276 petagrams of carbon is a huge amount of carbon. The total amount of carbon that had to be taken out of the atmosphere during the LGM was roughly 200, plus additions from the terrestrial biosphere as some of that carbon was transferred to the ocean. So this is more than accounting for the amount of carbon that was needed to be taken out of the atmosphere. But of course that was in a simulation where we kept atmospheric CO2 as at the same constant concentration. So in effect the atmosphere and the ocean weren't talking to each other. So we did additional simulations whereby the atmosphere and the ocean started to talk to each other. If the ocean outgassed CO2, then atmospheric PCO2 would increase. And if you increase the partial pressure of atmospheric PCO2, then it's going to be drawn into the ocean more readily. Similarly, if you were to in-gas, CO2 would be drawn into the ocean, then you reduce atmospheric CO2, and then the ocean is going to make the further uptake of carbon dioxide much harder, so that to actually maintain that in the ocean, because you reduce the partial pressure in the atmosphere. And so what you're seeing is the outcome of simulations whereby we've done that, whereby the atmosphere and the ocean talk to each other, and you're seeing the nitrogen fixation rate on the x-axis and the atmospheric PCO2 on the y-axis. And using this same circulation state, which by the way is representative not of the glacial period but of the pre-industrial period, you're seeing a bunch of different experiments whereby we've increased or decreased the relative amount of iron that's available to nitrogen fixers. So in the colours, that's represented by the colours. So the darker colours are higher amounts of iron, and then the lighter colours are lower amounts of iron that's available to nitrogen fixers. And you see that there's a large range whereby if you increase nitrogen fixation, it decreases atmospheric PCO2, and then if you decrease nitrogen fixation through a decrease in iron, you increase atmospheric PCO2. It seems to come out on this linear relationship, which has a gradient of roughly 0.5 ppm per 1 teragram of nitrogen fixation. This is consistent whether you actually physically increase iron or whether you just increase the relative amount that's available to nitrogen fixers. So nitrogen fixers are driving this increase and decrease in PCO2. But importantly, it allows us to quantify how much PCO2 could be taken up by the ocean if we increase the iron supply according to the glacial rate. And so that's the difference between the star marker and the plus marker. And what we find is that under this certain circulation state, which is representative of pre-industrial, remember, we get roughly 10 to 12 ppm taken up. So this is not insignificant, right? It's roughly 1/10 or 1/9 of the total interglacial change in atmospheric CO2. It's on the upper bounds of the amount of atmospheric CO2 that can be taken up according to iron deposition relative to other studies that I mentioned before. So if you were to put, say, this together with the previous studies, you might think that upper bound 20 ppm could be due to atmospheric deposition of iron. But of course the glacial circulation was different than the pre-industrial, so it's a bit flawed to use the pre-industrial circulation to quantify this. And so what we did is we took a bunch of different circulations to try and see what the effects of circulation and changes in conditions such as cooling how that could affect nitrogen fixation, and therefore this relationship between nitrogen fixation and CO2. And so what you're seeing here is the 4 different circulations we used, going from the orange to the black to the grey and to the blue, following the arrows anti-clockwise. What we notice is that if you look at the top at the T equals signs, it goes from warm to cold. So this is going from warm interglacial periods to cold, deep glacial maxima conditions. At the same time, you're also going from very well mixed conditions to poorly mixed. So that's represented by the radiocarbon, which is the shading behind them. So the radiocarbon is a measure of, if it's more depleted, the older the waters are, effectively. And so we're going from very well mixed young water throughout the global ocean. By the way, the y-axis is depth, and then the x-axis is latitude. I should have mentioned that. And so you're kind of looking at the ocean as if it were a bathtub from the side on. And so what you're seeing is that as you go from the warm to the cold conditions, you're seeing basically an aging of the ocean, so a slowdown of the overturning circulation rate. And at the same time, you're also seeing a increase in stratification, represented by these contours of isopycnals. And so we can play the same game where we do the same experiments that we did previously with the pre-industrial, the black circulation, which is our pre-industrial best estimate, and we can play the same game with the warm scenario. And we find that nitrogen fixation increases and decreases over a much wider range, as does atmospheric PCO2. The gradient stays roughly the same, 0.5 ppm per teragram of nitrogen fixation. And the difference between the modern and the glacial iron supply increases to 16 ppm, so it amplifies the response. And the reason for this is twofold. Nitrogen fixation is greater because it's warmer, but also because the spin-up of the overturning circulation, the increase in the rate at which waters are being overturned, increases the amount of phosphate which is being delivered to the surface ocean. And so a less stratified ocean increases the potential for nitrogen fixation. Phosphate supply, I like to think about phosphate supply as setting the potential for nitrogen fixation and therefore atmospheric CO2 drawdown. But then iron supply modulates that. It realizes to what extent that potential is realized. So if you plot all the different circulations from warm to cold on here, and you look at the table on the left, you'll see that from warm to cold, the magnitude of PCO drawdown decreases. It goes from 16 ppm down to roughly 7 ppm. So under full glacial conditions, the mechanism is the same, despite changes in circulation, global changes in circulation, global changes in conditions, wind fields, everything. We find that the mechanism remains robust, but importantly that the magnitude is reduced. And that makes sense with our phosphate supply argument, because a more stratified ocean will have less phosphate supply to the surface. And so conservatively we could say, on the lowest end, we might say that 7 ppm of PCO2 can be taken up by the ocean according to this low latitude mechanism. That's still significant, given that what we found with previous studies is between 2 and 10, with a focus on the high latitudes in those studies. So through adding these dynamic this dynamic biological functioning, these variable C to P ratios, nitrogen fixes that have these various physiological abilities represented in this model, and by testing across different circulation states, we've effectively doubled the amount of PCO2 that we realise drawn into the ocean through ion fertilisation, and through this looking at the low latitudes specifically, and then also thinking about the high latitudes on the side. And so I guess if you take anything away from this talk, it would be this schematic where we have low ion scenario at the top and then high ion scenario on the bottom. Nitrogen fixation is represented in the yellow. So if you just look at the low ion scenario at the top, which is kind of representative of, it's representative of today, nitrogen fixes exist in the northwest and the southwest Pacific. There's a surplus of phosphate that upwells 10 to 15 degrees either side of the equator where the upwelling occurs, which is represented in the blue. And then we have this cross-section view on the right where we have shallow oxygen minimum zones with not a whole lot of carbon export through them. Under high ion scenario, we reduce the need of nitrogen fixes that nitrogen fixes have for iron, and therefore they go to a new niche, which is where phosphate is abundant and nitrate is low. And this tends to, over time, because these simulations are run up to full equilibrium state, over time the niche of the nitrogen fixes actually butts up against the upwelling zone, and they draw down the excess phosphorus, they increase the C to P ratios represented by the fatness of the squiggly lines, and there's a vertical expansion in the oxygen minimum zones consistent with what we know in the literature, which is well reproduced by the model, and we get this overall transfer of CO2 into the deep ocean. So the third thing that we can talk about is, it's all well and good to play our modelling games, but really we need to think about how this stacks up against this wealth of information we have represented by the Delta 15N records. And so what you're looking at here, for those who love nitrogen isotopes, this is the global distribution of isotopic records, and the colours represent the glacial versus late Holocene difference in the isotopes. For those of you who don't look at nitrogen isotopes or think about them a lot, I won't labour the point, but they're a complicated proxy in the low latitudes affected by denitrification, nitrogen fixation, etc., etc. But the main thing to look at here, actually, when you plot this, is to see that there's this west-east difference. So in the west, in the South China Sea of the Pacific, generally all the records show an increase glacial values relative to the late Holocene, and in the east we see this consistent decrease along the upwelling areas, the California margin, the Peru-Chile margin, and then in the equatorial eastern Pacific. So this is being explained in various ways, but what I wanted to try and do was to use the model to see if we could actually explain this using our simulations of ion fertilization. And so what we did was we added the nitrogen isotopes into geoscientific model development, following the methods of pioneered by Chris Soames, and we did the same simulations where we increase ion deposition via glacial scenario, etc., etc. Right? And so what you're looking at here is the results of that. The paleoproxies are still plotted over the top in the markers, but in the shading behind it, you're seeing the results in the model. And so what you find, broadly speaking, I would argue, is this west-east reproduction of the isotopic values. So in the west, there's an increase in the isotopic value, and this is due to a decrease in nitrogen fixation. Remember, nitrogen fixation moves from the northwest to the equatorial eastern Pacific in the simulations. And in the east, though, it's not associated with the decrease in denitrification as classically interpreted since Ganestram in 1995. It's actually due to this increase in the vertical extent of suboxic zones causes a spin-up of denitrification, and the decrease is due to the increase in nitrogen fixation locally, which introduces low values, but also an increase in sedimentary denitrification over water column denitrification. Now, for those of you who kind of get into this stuff, that may be interesting. For the rest of you who maybe aren't super interested in nitrogen isotopes or paleoceanography maybe, all you need to know, I suppose, is that the model reproduced the paleoceanographic evidence, which, for me, I think that's pretty cool, and I think it's the best we can get, really, in terms of paleoceanography. And so I'll just end with some lessons and many good questions, right? So I think one lesson from this is that despite a lot of really constructive, I think, debate in the literature, shown here by some debates back and forth, I think dust-borne iron fertilization of the low latitudes is a thing. Second, low latitude and high latitude responses to iron deposition are complementary. You could actually think about the potential for them to be synergistic. So, for instance, if you were to increase iron deposition to the Southern Ocean, that would increase nutrient utilization. You could change the ratios of nutrients that are then exported in subantarctic mode waters, which would then have a follow-on effect to the low latitudes, possibly stimulating nitrogen fixation if you were to reduce the amount of nitrate relative to phosphorus in those waters. Or, you could change SI star and change the amount of carbon, organic carbon relative to inorganic carbon via the silicate leakage hypothesis, etc., etc. So I think these low latitude and high responses are complementary, and we should think of them as such. And then another nice thing is, I think, from this is that the complementary response requires relief from, on a global scale, from iron and nitrogen stress. And this fits in nicely with recent studies on the boundaries of upwelling zones and throughout the global ocean, showing that iron and nitrogen stress is pretty ubiquitous. So, some questions though that maybe for some of you. What happened to the global nitrogen cycle during the glacial period? Since the interpretation, the classical interpretation of low values in the glacial period in the denitrification zones, we've thought that the global nitrogen cycle slowed down, that there was less denitrification, there was less nitrogen fixation. In this study, I show that although there's cooler temperatures which slow nitrogen fixation, there's an increase in the rate of denitrification due to deoxygenation. And so that actually spins up the global nitrogen cycle to rates that were similar to the present day. And what does that mean for global nitrate concentration? What does that mean for Southern Ocean delta 15N records? So if there's higher mean delta 15N due to, say, a change in denitrification, does that mean that we need to change our interpretation or modify our interpretation of utilization in the Southern Ocean? Maybe that's not the only thing that's affecting the isotope records there. And then finally, how can we reconcile less particle export through excess barium and thorium studies in the Pacific with more carbon export in the tropical Pacific, which has also been shown by numerous studies? And I think the answer there is probably a mixture of deoxygenation, increasing the transfer efficiency, like I talked about, and variable stoichiometry, which is an increase in C to P ratios. So if we return to the puzzle, and we kind of think about the 30 ppm due to biological changes of these deep glacial maxima, which really underpin our understanding of the global carbon cycle going forward. I think we can say that some of this is due to dust-borne iron, and I would suggest that the combination of the high and low latitude mechanisms make it roughly 20 plus or minus 5 here. I've just put that there as a kind of my estimate. And then if you talk about alkalinity shifts and temperature-induced decline in mineralization rates, then you could bump that up to 30, 40 ppm. So again, we have the magnitude, but it's about putting the pieces of the puzzle together. And I hope that I've convinced you that this study tries to put, by making the low latitudes a valid mechanism, we can put the low and the high latitude response to dust deposition under the same umbrella, I suppose. And with that, I will take some questions, I think, if I can get this to work. Where's my phone? Where is it? Alright, I think I'm on. I think I can see things. Yeah, I think I've got it on my phone. I'll go to the Twitch. Yeah, so Al and I have been looking at, Eric, hello Eric. Eric asked whether we've been looking at future changes. I wonder, is my echo on? Maybe I'll get rid of this. Yes, okay. So Eric asked me whether I have been looking at future projections. So I alluded to that at the beginning. Al and I have been looking at doing some forward simulations under the RCP 8.5 scenario using Nemo-Piskus model, and we found that the isotopes, so nitrogen isotopes, are really a sensitive detector of changes in net primary production and other ecosystem shifts. So if you do time of emergence calculations on the isotopes, you find that they emerge well before nitrate and well before any other biogeochemical variable, oxygen, etc., and even well before temperature. But that's specifically not in the surface, but in the twilight zone. And the reason why we focus on the twilight zone, which is in the upper, say like 200 to 400 meters in that depth bracket, is because there's very low variability. So the signal of climate change that affects upper ocean ecosystems, that then transits down into this mesopelagic twilight zone, is very strong. And so we find that we're going to use the nitrogen isotopes as a sensitive detector of ecosystem change going forward in the next few decades. That's what we're proposing. Because, of course, I mean, the background to that as well is because the nitrogen isotopes are really, they're strongly linked to biology. Their nitrogen cycle is totally controlled by biology. So it's kind of nice to look at, if you want to detect biological changes, you should use the nitrogen isotopes. Does all nitrogen fixation require iron? yes, I would say. It requires other elements as well, vanadium, molybdenum. But I think the physiology of nitrogen fixes, I think the breakage of the triple bond of the dinitrogen gas does require iron atoms. At least that's what I'm familiar. That's what I have read. But I could look into that more. So can non-isotopic methods be used reliably in the model for future projections? Do you mean for detecting ecological change? Yes? Okay, sure. Okay, yes, I suppose so. Our argument in our research is that the isotopes are useful as a vehicle for understanding changes in the ecosystem because they're highly sensitive. So you could certainly look at they're also measurable, right? So, I suppose you could look at MPP just itself in the model and then project MPP, net primary production. But how do you actually measure that in reality? You can't. We can use chlorophyll A from satellites, but that's not actually a direct measurement of MPP, and actually it's quite a poor one in a lot of regions. Whereas if we can measure the isotopes directly and at scale on hydrographic surveys, and so I think they could be quite useful for that. But it's all tied together. It's one ocean, so maybe that wasn't a very satisfying answer. All right, well, thank you, David. And yeah, thanks for inviting me for the seminar series.